In this video, we are going to learn about some of the fundamental concepts of differential geometry. We are going to look forward into the concept of smoothness, what is called a smooth manifold, what is a differential manifold, and what is diffeomorphism. I'm going to keep it simple, intuitive, not much of mathematics or equations involved in it. I will be using a lot of graphs, charts, maps, illustrations, figures, so that you can understand all those concepts on a very intuitive level. There will be less amount of mathematics involved. I will keep it fairly simple, straightforward and easy, but we will go and understand the root of those concepts. My name is Shaunak and you're watching this video from Physics for Students. Welcome to my channel. Before we go ahead and understand more about those concepts, first about what are the topics that we are covering. So we are covering to know what is called smoothness in mathematics. Why do we at all need smoothness? What is smooth and continuous function? What is called a differentiable manifold? What is a C-infinity function? And what is diffeomorphism? So these are the topics that we are going to cover. We are going to keep it simple, right to the basics, not much of mathematics or not much of difficult equations that we would use, but we will understand those concepts and get it absolutely clear. So before we go ahead, the first thing that we understand is what is smoothness in mathematics. Now, if you have looked into my earlier video, this one, I have shown that we ended that video when I was explaining about Riemannian metric, and there were terms like smooth manifold, smooth, etc. So these are highlighted in red just to make you understand that this is the last video when we were talking about smooth manifold. And what is smoothness? I defined that it is a number of continuous derivatives it has over some domain. And I told that we are going to explain on what we mean by smoothness and continuous derivatives. And this is the agenda of today's video. This is the last slide and the last video that we ended on. So the concept of smoothness is everywhere around differential geometry. So you open up any book in differential geometry, you will also always find what is a smoothness. Okay. So first of all, let us understand what is the meaning of smooth, right? So if you see the basic idea of smoothness, that is the old English term, it would basically mean smooth. Okay, it also means smooth, serene and calm. I mean to say it would be free from roughness. It also means pleasant and polite and sincere. It also means something which is called a late English smop. So it is used in different ways. It means superior, classy or clever. To make smooth, smedian is smoothen. So all in all, these are the different terms in Old English and otherwise, where the overall idea of smoothness is to make smooth or relatively superior, classy, serene, and doesn't carry much of I would say bumps or phases like that. So just note that in literary English, what do we mean by smooth is basically what we call, it is an adjective, right? So smooth is definitely an adjective, and what it defines is a quality. So the question is that if smooth is used as an adjective in English, so are we using smooth as an adjective in mathematics also? So the answer is yes, because here smoothness describes the nature of the surface or the plane, right? So this is what I mean to say, that it is being used as an adjective in literary sense, and here also it is used to describe the nature or surface of plane. Okay, so in general in mathematics, if I take it forward, so smoothness of a function is a property measured by the number of continuous derivatives it has over some domain. We will explain what we mean by continuous derivative. Here is something: a surface is smooth if it is locally homeomorphic to an Euclidean plane. So let me demonstrate what do I mean by that. Now here is a diagram where you can see on the left hand side I have shown a sphere, right? And here there are people who are standing. I mean to say they are actually moving from one place to another. And if I map that and if I display that on a local plane where the same type of people are moving from one dot which is connected with the red with its arrow one, then you will see that it seems to them as flat. So the globe or the global part of the people moving are resembling that of locally. So that which locally resembles Euclidean plane or a space in near each point. So if I take this kind of a surface, right? You see a sphere and then a cylinder. So what I get is that these white things, let me show you again, these white boxes, right? These are the boxes which we are able to differentiate, and we can use this on the real number plane, which is Rn, and where the real numbers are x1, x2, x3, and it goes up to xn. And this is the sign which tentatively means that this is homeomorphic, right? So if f is continuous and its inverse, f inverse is also continuous. Just to demonstrate, right on your screen, you will see there's a, so the torus is turning into a mug, and now this mug will again go into a torus. So the torus again going into a mug, and then the mug is again going to a torus. So when the torus is a function f, right, this is the function f, this is continuous, and now when it is turning to a mug and the mug is turning back to the torus, so the inverse of the function is also continuous. So this is what I'm trying to tell you, is that when we say that the surface is smooth if it is locally homeomorphic, so homeomorphic means if I plot a kind of a function, the inverse of the function is also true. Just in this case, you can see the white boxes actually maps that onto a local plane, which is a real number, just as the people are moving. So it is also something which is local. So you can see this animation just to demonstrate that the function and the inverse of the function is also continuous. Okay, so here is another definition of smoothness. So we call smoothness of a function is a property measured by the number of continuous derivatives, right? Okay, so what I'm trying to tell you is that a function could be considered smooth if it is differentiable everywhere. But what do we mean by continuous derivative? Continuous derivative means that the function is differentiable and its derivative is a continuous function. So a function could be considered smooth if it is differentiable everywhere, and it is said to be infinitely differentiable, and we will see it later. So first is that the definition of smoothness followed by what we call a continuous derivative. So continuous derivative means the function is differentiable, that means those boxes where we differentiated, and its derivative, that is the derivative which is found out of differentiation, let us call it d, is also a continuous function. So let us first consider that f, for example, if a function, if it is differentiable, then f prime, for example, is at some point of x0 is also continuous, right? So this is a kind of a nice demonstration of a differentiable function, and this one is also a differentiable function, where is the graph on the right hand side. You can see this is a non-continuous function. Non-continuous function because you can see there is a break. So if I again take a surface or on a plane like this, and these are the small dots, small boxes which we had differentiated. So again, what we get is this, which is called a differentiable structure. So a structure which can be differentiated is called a differentiable structure, and the function is differentiable and its derivative is also should be a continuous function. So we take a surface, we differentiate it, and we try to find out that whether the surface that we differentiated is something which is local, then we call that function to be homeomorphic, and that is something which is similar to the Euclidean plane. So if I get a line like this, which I have just drawn, and we try to find out whether it is a continuous derivative or not. So if it is a continuous derivative, then we call it as a smooth function. So I hope this concept is clear. The smoothness of a function is basically a property. You can call it as an adjective, where it has got a continuous derivative, and then we find what is called a differentiable structure, and if we find that something is continuous derivative, then it satisfies the definition of smoothness. Okay, so if you open up any screen on any book of the differential geometry, you will find these type of definitions: smoothness, this one for a smooth, this one, so it's a smooth manifold, maximal smooth anglers, all those. So this is just to show you that any kind of a proper book on differential geometry will carry the definition of smoothness. Okay. So what we get from here, if you go to the earlier slide, is that we found out a concept which is called continuous derivative. Now, when we call something which is a continuous derivative, there are two factors involved. Number one, that it should be differentiable, right? And the second one is what we call, it should have a continuous function. So what we get from here is that this graph, if you see, these are, the left one side has got a corner, so it is non-differentiable. The second one has got a discontinuity, so these are all non-differentiable functions. So you can say that when we say that something is a continuous function, so a function or a graph is continuous without any breaks or jumps, right? So that means we are able to draw the curve of a function without even lifting the pencil. Then we say that the function is continuous, right? Now, but in this case, if you see that this function is smooth, but not differentiable. Why? Because this has got it has got a vertical tangent. So I hope this concept is clear. The continuous derivative is something which has got two features. It should be differentiable and it should have a continuous function. So if it is non-continuous, I just showed you these are non-differentiable function. It should not be considered as a continuous function. So what we can say that a smoothness or smooth surface should be locally homeomorphic to an Euclidean plane. I think that we just showed it, and should have a continuous derivatives over some domain, right? So a function is infinitely differentiable at a point if its nth derivative exists at that point for any value of n. So alternately, a function is infinitely differentiable at a point if its derivative exists and is infinitely differentiable at that point. Now, it means that there is no limit often how we can differentiate such a function. So if we get a kind of a function, just I took a fictitious number s of f, sf, which is a smooth function. So it should be infinitely differentiable, and that is what is called a C-infinity function, which we will deal later in this video. The derivatives of all orders in domain in which it is said to be infinitely differentiable and referred to as C-infinity function. So once you take a derivative of a function, you get a new function. Sometimes you can take the derivative of the new function again and again, and if we can go on taking the derivative, we'll go on the second and so on, and the first one and the second one, you get the third derivative and so on. Let me show you one kind of an example. So it means that we are allowed to differentiate as many times as we wish. Very important. So a smooth function should be infinitely differentiable, which is called a C-infinity function, and we can differentiate it as many times as we want. And you have seen that one of the two features of smooth function, that it should have a continuous derivative that is continuous and infinitely differentiable. So if we consider a kind of an example, like for example the sine of x. So the first derivative would give a cos of x. The second derivative would again give sine of x. The third derivative would again give cos of x. The fourth derivative again will give sine of x, and this will continue till infinity. This is the most important factor, that it should continue till infinity, and that is why we call it infinitely differentiable. On the right hand side of the screen, if this is a kind of a smooth surface, I can differentiate once, twice, thrice, fourth, 5 times, 6, 7, 8, 9, 10, 11, so on, and it will continue, right? So this is the basic concept, what we mean to say that it is infinitely differentiable. Right on your screen there is a kind of a nice analogy. Okay, so what we do is that we need to understand why do we need smoothness. That means if we do not have a smoothness, what would be the problem? Just let us quickly have a look on that. Okay, so if we get a kind of a graph like this, and we get a kind of a curve like this, and we get 2 points which are A and B, and we can circle those 2 points A and B, right? And we try to differentiate those 2 points into a kind of a surface like this. So what we get, we can differentiate first time, the second order, the third order, and so on. So what it means that if we are going close, and as we zoom and get it closer and closer and closer, it seems to look flat, right? So the figure on the left hand side is the graph which has got 2 points A and B, and it looks much straighter in the vicinity of the point when it is being differentiated further and further and further and further, right? So we want that it should be differentiated infinitely. So this figure is also the same. So we get a sphere and we get some surface kind of a thing. We get a function u which is mapping to b, and it is being plotted to Rn, which is a real number. The graph which is a real number, right? So I showed this one as kind of a similar example that we should point those things to the locally differentiable graph which is a real number Rn, alright? So what are the advantage is that it is easy to calculate. Obviously, once we zoom and zoom and zoom and we try to find something which is flat where we can use calculus, it is easy. We should avoid bumps which are difficult for us to calculate, and in topology it helps us to map a neighborhood. So this is a nice kind of a funny example. So if you get a kind of a coffee beans which is the function of x, so the first order differentiation gives a little bit of powder, and the second order gives us a coffee cup. That means that if we further differentiate, we get a smoothness which helps us to locally differentiate and find out something. So if the surface is not smooth, what will happen? It will be difficult to calculate, and whatever we told will create a little bit of problem. So this is a kind of a just an explanation to let you know that why we should find out a smooth surface, right? So you can see this kind of a graph which if we zoom it further until we differentiate infinitely, we don't get a smooth surface. So it helps us to study the surface easily, and infinite differentiation makes a smooth manifold. I just told you that these are important because until and unless we zoom further, it would be difficult for us to get the calculation. So it's a kind of a nice graph which shows that this right hand side, we zoomed it and we almost found it flat. So it locally looks something like a Euclidean space, and we saw it earlier also. But I would like to draw your attention that there might be some questions which are going on your mind. Are all functions infinitely differentiable? Can a function be a smooth but also not differentiable? Can there be a continuous and differentiable function which is not smooth? And what is the relation between smooth function and continuous function? Now, the first 3 questions we are not going to deal in this video because it is out of scope. It will take a long time. You can put out your comments in this part and let me know what are your views on the first three questions. So we will deal with the last one, which is a smooth function and a continuous function. So we move on to the next part of our video where we are trying to find out what is smooth function and what is a continuous function. Okay, so smooth and continuous function. So we can tell something like this, that in mathematics we can tell a continuous function is a function such that a continuous variation, that means a change without any jump of the argument induces a continuous variation of the value of the function. That means that there are no abrupt changes or discontinuities. This is the first definition. When we talk of smooth function, you will see that is the one which has some continuous derivatives up to some desired order over some domain, which is denoted by the C-infinity function. So the continuous function is the one you can draw without lifting your pencil and which has got no changes, where a smooth function is continuous derivatives up to some desired order. So this is a continuous function. This one is a smooth function, but which is not analytic, right? So a smooth function is a function that has continuous derivatives up to some desired order over some domain. A function therefore is said to be smooth over a restricted intervals. So the number of continuous derivatives necessary for the function to be considered smooth depends on the problem. So this is not an analytic. I hope you understand what is a smooth, but it is not an analytic function. Okay, so we can see that the smooth function actually, the word smooth, precisely it doesn't work actually in mathematics. It means that something I would say is differentiable on an arbitrary number of times, right? So in other words, a function is smooth if it is continuous and there's a notion of how fast it is changing, and that it is continuous, and there's a notion of how fast that is changing, which is continuous, and so forth. So as many derivatives as we can take. So these elements actually defines what is a smooth function. If you take a continuous function, then we can see that continuous roughly means in 2 dimensions that we can draw a shape without lifting our pencil. For instance, the jagged surface of a saw is continuous, but it is not smooth, and it should not have any discontinuity. The basic purpose of using so much of definitions is that to make you understand clearly the distinction, I won't say distinction, the relation between what is a smooth and what is a continuous function. So here is an example. This is considered to be a continuous function. This is also continuous function. This is not continuous. This is non-continuous function. Okay, if we get this kind of a line, you all know that it is a non-continuous function. I would say this one specifically, it is called removable discontinuity. Those who know and studied about the features will see removable discontinuity is one, and the line is continuous except for one certain point on the graph that is in separate location like this, which is being shown. This is non-continuous and removable. This is also to be considered as non-continuous but infinity. So it is infinite discontinuity. So you can see the first is where one side of a function at a certain point goes to infinity and the other side also goes to negative. So, these are some of the examples just to show you that what is a continuous function, what is a non-continuous function. So let us see some examples of smooth function. So this is a function, this is a smooth function, this is also a smooth function. This one, if you are wondering, this would be plotted something like this, which you can see. This one on the left hand side, this is also a smooth function. This wise it is called as piecewise smooth function. That is, a function is called piecewise continuous on an interval if the interval can be broken up into a finite number of subintervals on which the function is continuous on each open subinterval and has a finite limit at the end of each subinterval. This one is a piecewise smooth function broken into distinct pieces, and on each piece both the function and their derivatives are continuous. Remember, both the function and the derivatives are continuous. So a piecewise smooth function may not be continuous everywhere. However, the only discontinuities that are allowed are a finite number of jumps or discontinuities. Okay. So you see that whenever we are talking of smooth functions, obviously when we are talking of function, the first thing that comes into your mind is what is a polynomial. So the first thing that you should remember is that, as I told you, that smooth is not a mathematical term. So it means that something is differentiable arbitrary number of times. Point number 2, which is very important, is that all polynomial functions are smooth. Third, what we see is that many smooth functions are not polynomial. This is also important. So functions like exponential, root over x, log are examples of smooth functions, but they are not polynomial. This is important. So another point is that polynomial have finitely many roots, while smooth functions may have infinitely many, right? So they might have finite root, but smooth functions may have infinitely many. The sixth point would be that polynomial functions tend to plus to minus infinity, the variable x tending towards infinity, but smooth functions can tend anything they want or to nothing at all. Smooth functions are nothing as such. So these are some of the very important points just to let you know what would be smooth function and polynomials. I will just try to examine this further with some of the examples. So first of all, we take a define f of x equal to 0, what is right there on the screen. The first example, we take the value of f of x equals to 1. So we get a kind of a straight line like this. And if you take fx equal to 0, this is also same. So this function is continuous except where x equals to 0. That means the limit, this one, doesn't exist. Right. So this is one example just to demonstrate you. Okay. So this is not continuous. Yeah, obviously. So we take the second example where f of x equals to 0 and f of x itself equals to x. So what happens is that we get this kind of a function, right? This kind of function. So what does it mean? That this function is differentiable everywhere except at x equal to 0. However, the limit, which is this kind of a definition, does not exist except at x equals to 0. These are examples just to show you how we get the figures, and it will be a kind of a visual. So this is something which is continuous, but it is not differentiable because limit doesn't exist. Okay. Further example, we see that f of x equals to 0, the graph goes something like this. So the derivative of this function actually exists everywhere, right? So what we see is that for the derivative for negative value of x is 0, and while the derivative of the positive of x is 0. So what it means is that the derivative of x is 0, as you can see directly from the definition of the derivative. So this is something which is continuous but differentiable only once. It's important. The next example, we see that the value of f of x equal to x cubed by 6 and f of x equal to 0. This is the graph which goes. So once again, the derivative of this function is the previous one. So at x equal to 0, you can successfully take 2 derivatives but not 3. So we call this continuous but differentiable twice, not thrice. Right? The last example what we see over here is with this value, and the graph that we get is this one. This is amazing, right? Because this function, it has got derivative of all orders, all the derivatives of f of x. So what we get, it has got derivatives everywhere, and this is infinitely differentiable, and since it is right. But there is a catch. If you get this kind of an equation, what we get is that the Taylor series of this function around x becomes useless, and this function is a C infinity function which is infinitely differentiable, and hence it is. These are few of the examples which will demonstrate the shape of the graph, the values, so that you understand which is differentiable, which is only differentiable once, twice, etc. Okay, so we come to the next part of our video where we are going to explain to you what is a differentiable manifold. As you can understand, the word itself differentiable suggests that there should be some kind of calculus involved in it. So I would use the old method of plotting a sphere along with some people standing. He's going over this place, is again moving to this and this and this and this and this and this. So it keeps on moving from one place to another until it ends somewhere here. On the right hand side, what we get is a kind of a, you can call it as a graph or a surface, something like this. So what we do is that we plot those same people on a local plane where you go this and this and here and here and here and here. So it completes. So what I'm trying to show you is that this is something which locally resembles Euclidean space near each point. Alright. So we mean that it looks like, gives rise to the different notions of topological manifold. Anyway, so what we mean by local is that the general idea we want to consider is that it is in the vicinity of a given plane or a given point. Right. So what we get, this is a global one and this is a local one. And these are few of the definitions which you can read it out. A differentiable manifold, also a differential manifold, is a type of a manifold that is locally similar enough to allow one to apply calculus. So once we apply calculus, it becomes easy for us to do the calculations. A differentiable manifold is a generalization to higher dimensions of the concept of a smooth surface in three-dimensional Euclidean space. This is quite pertinent because we have just read what is a smooth surface, and differential manifold is basically we are generalizing and extending it to higher dimensions. A differential manifold is a topological space which is locally homeomorphic to a Euclidean space. If you remember right at the beginning of the video when I showed you the example of a torus and a coffee mug that was locally homeomorphic and such that the gluing function it relate to these Euclidean local charts to each other, differentiable functions for a fixed degree of differentiability. So anyway, this is just to give you an idea that what are the definitions what we call a very differentiable manifold. So if you take those things further, what we get is that on a sphere when we move, these are what is called a positive curvature. This is somewhere nowhere it is going, so we call it a zero curvature, and this is what is called a negative curvature. So what we get, if you get this kind of a surface and we get these boxes, what I'm trying to show you is that we use calculus and we apply the rules of calculus and differentiate those, and this is what we call this locally looks like a ordinary piece of Euclidean space. Just an analogy that when we analyze a manifold, how do we get above it? Okay, so let us define a differentiable manifold in a mathematical way. I've just laid out a very simple figure, right? We call this a map. This one is the map. It's a continuous map phi, a chart around the point x at M. So if you talk of chart, intuitively you think of a chart as like a page on an atlas. It gives you a flat approximation of a small piece of your whole surface. This is a chart around a point x, and a chart is like a page of an atlas. It gives you a kind of a flat approximation of a small piece, and it is an atlas consists of individual chart that covers the entire manifold. So chart, and then it gives to an atlas, right? So this is, now let us see how do we go from this. So we take the same chart and we try to find out these two ones. So right, you see this this phi and psi. We have taken these two functions. So these two, when we take them and we try to find out a point where these two charts intersect, right? Well, having all these charts is helpful. It is much of use until we have some way to go from one chart to the other. That is it, we start in one chart and move along the line, right? So if we try to get this one, let us see, this is the common place where those charts intersect. So we plot another kind of a figure where we are taking this common point over here. Can you see this one? This blue one is going to the common cutting point, and we are plotting the same thing over here. And this is what is called a transition map. I'm not going to explain further about transition map. It's totally different subject. So what I'm trying to tell you is that while having all these charts is helpful, it is not much of use until we have some way to know how we go from one chart to the next. So if I start in one chart and move along the manifold, I need to tell some way how I can transfer my coordinate system to a different chart. So this is the cutting point. It's a common intersect we have plotted over this. Just remember that this is not a dot product. This is a composite function. So this is when it is a composition of two homeomorphisms. So what we get is that a map between Euclidean space formed by the composition. This, okay, so you got this one, right? So this is some kind of a clearer picture. So this is, I just take it from NCAT. So it actually shows you. So what I'm trying to show you is that mathematically when we talk of a differential manifold, we are trying to map, or we get a chart and we map the common factors which are coming. Remember, it is a two-dimensional charting mapping into this. So it gives you a clear picture. Okay. So if you get this one, and once we when we move to this part, so this M, this is the manifold, right? So if it is a map from Euclidean space to Euclidean space, it makes sense for this to us. Now, since it's a map from Euclidean space, so what we get that M has the structure of a topological manifold. Now, if you ask the transition maps, are they differentiable? Yes. Then M has the structure of a differential manifold. And if you ask that whether there is an isometry between them, then we make that yes, N is a Riemann. Right. So what I tried to show you is that what is differential manifold, I mean to say, in terms of mathematics, when we are using those charts and we are mapping the M into two different maps, and this is what we call, which is a differentiable manifold, which is a topological manifold, a structure of a differential manifold, as well that of a Riemann manifold. Now, the obvious question which comes to your mind is that, is smooth manifold the same as differentiable manifold? It's a very pertinent question that comes to our mind. I would like to ask you that, if I ask you that, how low is low? And it's LOW. So what will you answer? Right. So a smooth manifold is a special type of differential manifold. So smooth means infinitely differentiable, right? While a differentiable means differentiable as many times as specified. Whatever, it does kind of a specification. Now, it also means that once it is differentiable manifold, twice differentiable manifolds, infinitely many differential manifolds, and so on. So, the 2- and 3-dimensional topological manifolds have a unique smooth surface. I would say it will be 4 dimensions, and it has become a hell of a work to break it up, right? So, a differentiable manifold, I would say, is equipped with an equivalent class of atlases. Those transition functions are all differentiable, and a smooth manifold is differentiable manifold, which has got a smooth transition maps, which we just denoted that we use it with the round, that dot one. It's not a dot product, it's the composite function we use it to. So, this is something, very important, that a smooth manifold, infinitely differentiable, what is that? And these are the important points that we can keep it in mind. Okay, so we come to almost the last part of our video, where we are going to explain what is diffeomorphism. Well, the word itself suggests it is a combination of differential and morphism. So morphism will be there and differential will be there. So if I talk of diffeomorphism, the definition. So a diffeomorphism is a homeomorphism which preserves the differentiable structure on a manifold. We will explain what are those. In mathematics, a diffeomorphism is an isomorphism of smooth manifolds. It is an invertible function that maps one differential manifold into another such that both the function and its inverse are differentiable. So, few things which becomes extremely important out of this definition is that we have already understood that diffeomorphism is definitely a homeomorphism, right? And it is also a kind of an isomorphism. First of all is that it preserves the differentiable structure. Now, I don't want to extend right now, but this point of preservation becomes very true in terms of general theory of relativity. Because when we are taking arbitrary spaces and we are trying to calculate those structures and curvatures of space-time, preserving the differential structure becomes very important. What becomes important also is what is an invertible function and what do we mean by maps to one another. So we will take these three components one by one. What is preserving structure, what is invertible function, and what is meant by mapping. Once we understand these three, then the concept of diffeomorphism is as clear as a glass of water. Okay, so what do we mean by preserving the structure? The left hand side figure actually is a rectangle. It's a 4-cycle rectangle. And the right hand side figure here, it is a kind of a twisted rectangle, right? So in the sense of connectedness, these both graphs are structurally the same. But how we say this in terms of mathematics? So we begin by introducing a notation of connectedness. We write this one. Okay, so we can call it isomorphic, similar, whatever, it doesn't matter. But the basic concept is important. So I call it V1 is similar to V2, right? For the facts of node V1 and V2 here in blue are connected by an edge. On the other hand, V1 is not isomorphic or similar to V3 because V1 is not connected to V3, which I just showed in blue. Now we want to say that these both the graphs are same. We can show this by giving way how to transform the left from the right. This can be done by stating which vertex on the left can be mapped on the vertex on the right, which we have shown. So we do this via map F, which is a kind of map. For example, we say this one. So we take F as a map and we say F of Pi is equals to Wi. This specific transformation is not structure preserving because of the following sense. V1 is isomorphic to V1, V4, but the map of V1 is not isomorphic or similar to V4. So this is one. So we will take for So you see that W1 and W4, they are not isomorphic. Because when V1 is being mapped to W1 and V4 is mapped to W4, then W1, V1 would not be isomorphic to V4 once it is being mapped. Right. Before, when it is not mapped, you see V1 and V4 could have been isomorphic because these two nodes connect. But once this has been mapped using the F mapping point, V1 is not isomorphic to V4. Okay, so let's go forward. We'll say take the same kind of a structure. So just mapping each vertex with the index on the left to corresponding vertex with the index on the right will not give us the transformation. So we can see with this failure we need to claim okay, so yeah, simply mapping each vertex really doesn't work. So what we get is that we need to claim that V1 is isomorphic to Vj, which implies that the mapping of F of Pi is isomorphic to Vj. How we are going to do that? So we take this kind of a figure, right? Now let us watch it closely. So here I map V1 to W1. I map V3 to W1. I map V2 to W3, and I map V3 to W3. Right. So many different nodes can be mapped to the same node as long they are not connected. Why? Because a node in this kind of a graph never connects to itself. So we can obey the homeomorphism rule. So what we actually find here is that the right hand side, the lower side subgraph consisting of vertex W1 or W3 is somehow structurally, so many different nodes cannot be connected. Nodes are connected by itself, and vertex W1 and W3 are structurally similar to the left. And as we have seen that V1 was not isomorphic to V3, and here I prove that W1 is isomorphic to W3, so it implies that V1 is isomorphic to V3. So this is what we call a kind of a structure preserving by connecting different nodes. So this is the part one element of what is called preserving the structure in terms of diffeomorphism. So you saw how we map those nodes, and once these nodes are being mapped, we show the structure preserving part. Okay, so I think we all know what is called an invertible function. So invertible function, is something that the functions that reverse each other. So for example, if f takes from a to b, then the inverse of f also takes from b to a. Just demonstrated. You can also use this one. This is also true. I mean to say, this is also kind of a function. So a mapping to 3, b mapping to 1, c mapping to 2, and it is the inverse is also the same. Okay, so we take this I will just explain why I have shown this. So it is an invertible function that maps one differential manifold to another such that both the functions and their inverses are differential. For example, if I take this kind of a figure, right? So you can see the phi over there, the psi. So this is diffeomorphic. Why? Because here the line goes from this to this, and here the line returns from this to this. So it is an invertible function, that is like the inverse. It is mapping one differential manifold to another. The nodes which we connected, I just wanted to cite an example. These nodes are also connecting to each other. So now we have understood the second component of diffeomorphism. What is an invertible function? So once we are mapping one part to another, the function and the reverse function should also, take to each other. So what we can say is that a circle and an ellipse, right, they are diffeomorphic. So remember, a homeomorphism is simply a continuous function between topological places, right? Spaces. But to make a diffeomorphism out of homeomorphism, we simply add an extra condition that the function and its inverse will both be smooth. So in case of a homeomorphism, you have seen that the function is continuous and the reverse function. But here, in case of a diffeomorphism, what we say that the function and its inverse, the inverse part, is also to be smooth. So let's see further examples. So we can deform a circle into an ellipse, yeah, just by smooshing that. And we can also, it is an invertible function, so it can come back to that part. So for example, a circle, this one, and a triangle, these are not diffeomorphic. Why? Because it has got sharp edges, right? With diffeomorphism, we cannot. So let us consider, for example, a mug and a torus, right? So a mug and a torus, they are homeomorphic, but they are not diffeomorphic, because the handle of the mug is not adjusted in such a way that it could be differentiable. Or you can say, for example, a cube and a sphere are homeomorphic but not diffeomorphic. So in order to say in a simple word that homeomorphism is basically a bijective mapping in the category of topological spaces, and diffeomorphism is the bijective mapping in case of category of differential. Okay. So what we got is that we got the mapping of one differential manifold to another. This is the one and this is the one. So that would give you a kind of a clearer picture of what it is. So it's bijection and it's so if you want to define the mapping of one another, so we get this one, mapping of one differential manifold to another. So we get M and N. So we get M is called a diffeomorphism. So in mathematical, diffeomorphism is an isomorphism of smooth manifold. So if given two manifolds M and N, a differential manifold is called a diffeomorphism. If it is a bijection and its inverse, this one is also differentiable. This one, now if you say that if this function are S times or R times continuously differentiable F, then F is called CS times diffeomorphism. Just to let you know, so two manifolds M and N are diffeomorphic, which are usually denoted by this, right? There is a diffeomorphism F from N to N, and they are C that times diffeomorphism. Okay, so yeah, so diffeomorphism is an isomorphism of smooth manifolds. So finally, we come to the last part of the video. So we have understood what is diffeomorphism, and we have seen what is structure preserving through this. It's a kind of just an analogy just to make you understand what is structure preserving. We have also seen what is the differentiable structure, this one, which we can use calculus and differentiate and up to infinity. We have also seen what is an invertible function, that the function and the reverse should be continuous with diffeomorphism. And we have also seen what is mapping one differentiable manifold to another. This is the one, and we use what is called mapping from one manifold to another, and we call what is called a transition map. So this completes our understanding of what is diffeomorphism. We come to the very last part, which will just take a few minutes to explain what is a C infinity function. So C infinity function is nothing which has got calculates the smoothness of a function because they have no bumps, measured by the number of continuous derivatives, infinitely differentiable, which is called C infinity. So here you see this one, this function is continuous, and this is goes up to C infinity, whereas this function is not continuous because they have no bumps. So sorry, I showed it a little bit earlier, but this is the result of C infinity. So C infinity is nothing more, I mean to say, it will be calculating the smoothness of function, its continuous derivative up to certain level of infinity. There is something which is called C to the power k function, or integer positive. I am not going into that. Okay, so that completes our video today. So what we learned is that we learned what is smoothness in mathematics. What is smoothness? We learned also what is the origin of the word and etc. Why do we need smoothness? We don't have a smoothness, we run into difficulties, problems. what is the relation between smooth and continuous function. We also found a lot of important points on smooth function and polynomial functions. We demonstrated a lot about differentiable manifold, how these things look like, what is diffeomorphism, taking three important elements or components of the definition, and what is called a C-infinity function. Well, I know it has been a long video, but these are important concepts in order to get a hold of differential geometry. So in the next video, we will be speaking about submanifold, immersion, exterior product, differential form, and manifold which has got no boundary. So that's all from my side. I hope you enjoyed the video. I know we covered a lot of concepts. It took a little bit longer time. This is important. Stay tuned to come up with more videos on differential geometry, and I'm coming up with more surprises which I'm not going to announce right now. Stay tuned in Physics for Students. This is Shaunak signing off, and wish you a very happy learning and wish you a safe, wish you everybody wherever you are, stay safe and stay happy. Thank you very much and wish you all the best. See you very soon. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.